Okay, so perhaps we can begin. Yes, so welcome everybody to this week's Majorana-Raychaudhuri seminar series. Our first talk is by Aurora, Ireland from Stanford University, and she is going to talk about cosmological phase transitions in CMB BB mode polarizations. Maybe I'll send a reminder when 5 minutes are left.
Okay. Start sharing them.
Yes, we can see.
Perfect. All right. So thank you for having me, and sorry in advance. It's a bit early here, and I'm not 100% awake. So if I say anything wrong, please correct me. But I'm excited to tell you today about this work that I did with collaborators Gordon Konjaik, Yusin Tsai, and then Kyler Green on CMB B-mode polarization from cosmological phase transitions. And I want to start with a quote, and I just pulled it from a random paper. Well, a nice paper, but a random paper. But you'll see sentiments along this line in many papers. So tensor fluctuations are a prime target for future observations of the CMB because if detected, they can provide conclusive verification of the theory of inflation. Or more succinctly, B-mode polarization in the CMB is a smoking gun for inflation. So pretty generically, most inflationary models tend to predict this nearly scale invariant spectrum of tensor perturbations, and these induce a characteristic B-mode polarization signal in the CMB. There are, of course, other sources of B-mode polarization, namely gravitational lensing can convert an E-mode pattern to a B-mode pattern. Also, if you have any sort of foreground contamination, like polarized dust or synchrotron radiation, that will also complicate the signal. But really, inflation is the only well-accepted direct primordial source. And it really doesn't matter that we have these other sources because the spectral shape is pretty distinct. So here I have a plot of the angular spectrum of B-mode polarization. Well, there's also E mode and temperature on here, but we're going to focus on the B mode. So these are two predictions from some theory of inflation that gives a nearly scale invariant spectrum with a tensor to scalar ratio of 0.03 and 10 to the minus 3 respectively. And then contrasted with that, we have the lensing B mode signal, which tends to peak on much smaller scales. And then I also have some data here from BICEP and SPT and ACT and polar bear. So if you do observe a signal, it can be delensed, and really the ultimate goal of these upcoming observatories like CMB Stage 4 and the Simons Observatory and Lightbird will be to hopefully either observe or constrain this tensor to scalar ratio a little bit better. So these are the known well-accepted sources, but in principle, really any source of large scale coherent tensor perturbations, if they're produced before reionization, can contribute to B-mode polarization. And the source that we explored in this paper is first order cosmological phase transitions. So these proceed via the nucleation of true vacuum bubbles in the metastable phase, and they naturally source anisotropic stress and therefore tensor perturbations through, first in the bubble collision stage, and then in some acoustic phase, and then later in turbulence. So, I mean, this is generally when we think about cosmological phase transitions, they're things that happen in the early universe. And so you're going to predict peak power on kind of small scales. And on larger scales, you're just going to get this white noise spectrum, which is kind of characteristic of any sort of causal subhorizon physics producing your tensor perturbations. And so naively, because of this, you would expect this contribution to be negligible. I mean, I certainly didn't think we'd be able to see anything from this. The reason being that, the CMB is sensitive to long wavelength stuff. large scales. So co-moving wave numbers around or less than 0.01 inverse megaparsecs, maybe actually a little bit larger than that, but on that scale. And for the phase transition, the issue is that power is going to be suppressed on these scales, because these modes, which are super horizon at production, in this regime of the power spectrum, which is going to be relevant for the CMB, the tensor power spectrum is going to go like k times tau star to the third, where here tau star is the conformal time at the time of the phase transition. So this is generally very small for super horizon modes. But surprisingly, so here are the two big takeaways that I want to try and convince you of. The first is that the amplitude of the B mode signal, if it's a late time first order, sufficiently strong first order phase transition, actually can be quite large and even kind of rival these inflationary predictions for the tensor to scalar ratio that we hope to constrain in coming years. And the other point is that, it's not hopeless. It's actually, the signal still, it looks different from inflation. So the scenarios can still be distinguished. As you might expect, the phase transition is going to give you more power on smaller scales. And ultimately the spectral shape is going to be distinct. So these are the 2 points I want to build up to. I guess that was the motivation. Next, I'm going to talk about first review how B mode polarization gets baked into the CMB. Then we'll review how you calculate the tensor power spectrum from a first order phase transition. I'll show some numerical results, touch on gravitational waves, which would be a complementary signature of this scenario, and then just conclude with some summary. Also, if you have any questions, feel free to stop me. Okay, so B mode polarization. Very generically in the early universe, if you have scalar or tensor perturbations, these are going to give you temperature anisotropies. And temperature anisotropies plus Thomson scattering is going to give you some sort of net polarization. So here's just a little picture of some incoming photon. You get some Thomson scattering with a free electron, and then it goes off with only one polarization because light, of course, can't be polarized along the direction of motion. So of course, there's no reason to just consider it coming in from one direction. If you have like a dipole anisotropy in the temperature distribution, this actually won't give you anything because the incoming radiation has equal intensity, so there's going to be no net polarization. What you actually need to get net polarization is a quadrupole anisotropy. So if you have like a hot spot and a cold spot coming in, and they Thomson scatter with this electron, the outgoing scattered radiation is going to be some net linear polarization. So quadrupole anisotropies come in, scalar, vector, and tensor varieties. Density perturbations will give you the scalar sorts. Vorticity will give you vector, but this is negligible at recombination, so we're going to forget about these. And then gravitational waves will give you tensor. And then if you project these quadrupole anisotropies, that's how you get a polarization pattern. So it's usually you decompose this into divergence and curl parts. So E mode polarization is the divergence part. This one is unchanged under reflection. And this sort of pattern is sourced by both scalar and tensor perturbations. Versus B mode polarization, this is the curl parts, an analogy with a magnetic field. This one is parity odd, and it's sourced by tensor perturbations only, which is why you have this statement that B mode polarization would be evidence of primordial tensor perturbations, aka gravitational waves. So quantitatively, the object we want to study is the angular spectrum of B mode polarization. So these CLBBs, and yeah, the computation to get here is kind of involved, and we do review it in the paper. And I mean, it's reviewed in a lot of textbooks, but at least to sketch how it goes. So we start out with some tensor perturbation, Hij. This is going to contribute to the temperature anisotropy, which enters into the CMB polarization tensor, it's PAB, which you can decompose into gradient and curl parts. We're going to focus on the curl parts. You can expand that in spherical harmonics, and then you invert that to isolate these ALM coefficients. And then if you take like an appropriate 2-point function of these guys ensemble average, you get your CLBBs. So more precisely, this is the formula for how we're going to get these. And if you evaluate this completely generically, this is the expression that you get. So you get this integral over log k of this curly piece of H. This is the dimensionless tensor power spectrum. And then this FL squared thing, which is this horrible thing, which I feel like I had to include this because it's where all the physics is hiding. We have like, a few factors of the visibility function, this combination or this difference of spherical Bessels, the transfer function, another spherical Bessel. Really the way to think about this though is just like a window function. Like it's a window function or a kernel that picks out the modes that the CMB cares about. So obviously where it's going to peak is going to depend on which angular multipole you're looking at. But, from 0 to a few thousand, very generally it peaks around 0.01 inverse megaparsecs. So this is where since this CLBB is like an integral over log k of this times this, obviously it's going to get its most support around those scales for like a scale invariance tensor power spectrum. And we'll see how a different shape of the tensor power spectrum fares. But yeah, at this point, this formula is fully generic. Sorry, one sec. Okay, so implicit when I did this, I've done this decomposition of the tensor perturbation into some initial amplitude times the transfer function. And the reason that I've done this is because it kind of separates the statistical correlations between the initial amplitudes, which are, model dependent and going to depend on your actual source. And they're encoded in the power spectrum, which is defined as this, appropriate 2-point function of the tensor perturbation. It separates out that from the deterministic evolution, which is captured by the transfer function. So the transfer function is just going to solve the approximately sourceless wave equation if we're kind of neglecting neutrino anisotropic stress. And you can solve in the radiation domination and matter domination regimes, and you just get, these combinations of Bessels. The behavior of this is, it's constant while the mode is inside the horizon. And then once you enter the horizon, it starts to decay and oscillate with some, appropriate Bessel behavior. And in practice, we're going to use class the Boltzmann solver for all our transfer functions. But this is analytically how to understand it. Right, sorry, that was a very fast review of how we're going to calculate the B-mode polarization. The ingredient that we're missing at this point is what this, the curly piece of H is, the tensor power spectrum. And so let's turn now to how to calculate that. Right, so I mentioned before, we're going to be looking at first order cosmological phase transitions. So these proceed through bubble nucleation. So some true vacuum bubble nucleates in the metastable phase, and then it starts to expand because of the latent heat, I guess, kind of pressure differential. And as it does so, there are kind of three stages, more or less, that it sources tensor perturbations. There's the initial bubble collision phase. And actually, it's not so much the collisions that are giving you the tensor perturbations. It's more that the collisions are breaking spherical symmetry, because you need to break spherical symmetry if you want gravitational radiation. And then once that happens, the gradient energy of the scalar field, whose profile is kind of defining the bubble wall, that gradient energy is the thing that's sourcing the anisotropic stress in this phase. So even after the bubbles have collided, you still are going to have these shells of fluid kinetic energy that are propagating through the plasma. And when these collide, these also give you tensor perturbations. This tends to be the dominant source for most thermal phase transitions. The bubble collision phase is only going to dominate for like nearly luminal bubble wall velocities, which you'll only get if you have a very dilute plasma. So for most thermal phase transitions, it's this acoustic phase that's going to dominate. And then finally, the sound wave collisions are going to give you vorticity or turbulence and shocks, and these will also contribute some degree of tensor perturbations, although this stage is definitely the hardest to get a handle on analytically. You really need these numerical simulations. We're just going to focus on so this project was kind of a proof of principle that you could even see anything, and for that reason, we only focused on one particular source of tensor perturbations. And I'll get to later why we chose this sort. But as a case study, we're going to consider a supercooled phase transition occurring in some dark sector. So by supercooled, I just mean that, the universe stays in this metaphase. It's exactly like supercooling in like more traditional phase transitions. Just the universe is going to stay in the metastable phase for past the critical temperature. And I guess technically all first order phase transitions are a little bit supercooled, but we're going to consider considerable supercooling just because then you get this dilution of the plasma. And because of the negligible plasma friction, then your bubble wall can go off to runaway velocities of, approaching the speed of light. And for this particular class of phase transitions, you get your dominant contribution from the bubble collision stage. So we're going to only concentrate on the contribution from this stage, just for the sake of being able to compute something. But honestly, I expect the signal from like a thermal phase transition to be very similar. In particular, just because most everything we're going to be doing with the tail of the spectrum. And as I've already mentioned, that tail is always going to have this k to the cube scale. Well, not always. There are some scenarios where you can get around the causality limited scaling, but for thermal phase transitions, from the bubble collision stage and the sound wave stage, they're both going to have the scaling. With turbulence, actually, you can get away from the scaling, but I've gone on long enough. Okay, so we're going to consider this source, and what we want to do is we want to solve for the tensor perturbation. So we're going to solve the source wave equation now. So here primes are derivatives with respect to conformal time. Curly H is my conformal Hubble rate. And then this pi ij is the source. And the source is, I guess, a Fourier transform of the transverse traceless stress tensor. It's also a statistically homogeneous isotropic random variable. And then the other thing we're going to assume about the source is that it's short-lived, just in the sense that the phase transition completes fast. So within a Hubble time. This parameter beta is the inverse duration of the phase transition. So we want this ratio to be greater than 1. So it's going to be short-lived in the sense that it completes within a Hubble time, but because it's supercooled, this will be closer to, 1 to 10 as opposed to 1,000 or higher that you would have for thermal phase transitions. So we want to solve the wave equation during the phase transition. Because it completes fast, we can make our lives a little bit simpler and neglect expansion. You can show that if you include expansion, you get essentially the same results. And in this regime, you can solve this via the method of Green's functions, and you get this expression. So integral over the source, which we'll specify in a second. And then after the phase, sorry, I should also mention that here I'm switching to this dimensionless k times tau variable, and now here primes are derivatives with respect to this new variable. Okay, after the phase transition, we can no longer neglect expansion, but we essentially have no anisotropic stress. Just a little bit of neutrino free streaming maybe, but to a good approximation this. And in this regime, you can solve this exactly to get this expression where these coefficients A and B you can determine by matching these two at xf at the end of the transition. So recall that we're defining the power spectrum as this 2-point function of the initial amplitude. So this gives me, this is a function of time, and naively you would think the initial amplitude is just Hij evaluated at xf. And indeed, for subhorizon modes, that is the case, but there's a little bit of a subtlety with the superhorizon modes. So we're gonna treat these two cases separately. I'll get into that in a second. First, for the subhorizon modes, though, there's no subtlety, and we can just define the initial amplitude as your Fourier amplitude of the tensor mode evaluated at the end of the phase transition, so at k times tau f. And in this case, if you take like the 2-point function of these guys, you can show that this is the expression you get for the dimensionless tensor power spectrum in the subhorizon regime. So here, this is proportional to this kappa, the efficiency factor, the transition strength alpha, which is the essentially the energy density, the vacuum energy density released over the energy density in radiation. There's a few different ways actually of defining this, but this is morally what it is, times h star on beta squared, times this factor, and then we've got this thing delta. And this is actually, I mean, this looks like a really nice, neat expression because all the mess is hidden in the definition of this delta. So this is where all the physics is. And the prefactor, I pulled out like the thermal phase transition parameters, which then appear here. And then we've got this double integral over conformal time of some cosine times pi. And here pi without the little indices is the unequal time correlator. So it's like, I should have written down what it is explicitly, but it's like the 2-point function of two of the source terms evaluated at unequal times. And this is really, we have to calculate this. Except we don't, well, we did, but the reason that we chose this class of phase transitions to concentrate on is because there's this really nice paper by Gino and Takamoto, where they compute this delta semi-analytically working in the thin wall and envelope approximations. And we check their results and also obtain the same expression for delta, which is encouraging. And it's, naturally this complicated thing, but you can fit it to like a fitting function. And then if you take
can I ask you something?
Yeah, sure.
Yeah. So this paper 1605, was it for supercooled phase transition or was it for generic?
No, it's completely generic.
Yeah. So I think for the supercooled phase transition, people have updated this, and this factor is different. I mean, not drastically different, but quite a bit different. There was a recent paper from 2022, like 2 years ago, I think. I can share, I can send you the reference.
Yeah. If you could share that, that would be great. I may have seen it. Do you remember who the authors are or what the title is?
Yes, my colleague Marek Levitsky from Warsaw, and then Ville Vaskonen from Padua in Italy and Estonia, Tallinn, Estonia.
Hmm. Okay, I certainly know the names, but actually I might not have seen this. Yeah, if you could send me that, that would be
Yeah,
great.
sure.
Um, yeah, and I mean, okay, so there, I have to with this. I should give a disclaimer, I guess, at this point that with the super cold phase transition that we're considering, we're going to consider values of beta on H that are kind of pushing the limit of is the phase transition actually going to complete? Is this something you can get from like a realistic particle physics model? And for me, all those questions are secondary to just seeing, can you get any sort of signal at all? So this was kind of the preliminary. This paper was kind of the preliminary step here. And now, as a follow-up, we're looking at those questions and looking at if you actually do this in an expanding universe, you get similar magnitudes. And I guess now I'll look into this paper you're describing, but just as a first pass, let's just take it to be this. So if you do, then in the subhorizon regime, you can show that this has this approximate scaling, and obviously in the actual paper we'll use the exact fitting form, but if you do this approximate scaling, then this is the expression you get for the subhorizon spectrum. So yeah, I'll plot this in a slide or so, and we'll see. But first we need to handle the superhorizon regime, and this is where a subtlety comes in because activating a superhorizon mode, it's kind of like exciting an overdamped oscillator in the sense that it's going to take a little bit of time, a small but finite time, for the mode to grow to its maximum amplitude, because the initial conditions are such that H is 0 and the time derivative is non-vanishing. And because of that, we can't define Hij as just, or sorry, the initial amplitude is just the tensor perturbation evaluated at the final time. We need to wait this tiny time interval, which you can see if you plot this, and maybe I should have plotted this. The reason that this is important is because we've done this kind of artificial decomposition of Hij into some initial amplitude times the transfer function. And we want to make sure that we're applying the transfer function once the mode is like, it's an initial frozen out amplitude, because the transfer function is just going to be constant until the mode re-enters the horizon. This is, something that we apply that in class, and we want to make sure that we feed it the initial power spectrum at the point where the mode has, grown to its frozen out value. So that's the reason for that. And you can show that if you do this, this is the expression that you get for the tensor power spectrum in the superhorizon regime, which looks an awful lot like the subhorizon one, except there's no AH on K squared factor. That's the only difference. Of course, the other difference is that in this regime, in the superhorizon regime, this delta takes this approximate form, and so this is what we get for the tensor power spectrum. So I guess there's two main things I want to say with this. One is that you get the expected k to the cubed causality limited scaling, which you're always going to get when, if you have some source that has correlations in real space only up to some point when you Fourier transform that, it's obviously going to have supported all k values, but for small, k values, it's going to go like k to the cube. So that's white noise. So the correlations on superhorizon scales, aren't really correlations at all. It's just noise. So that's, consistent with causality. And then the other thing that's I want to say is that this is going to be suppressed because this k tau star, which is x, it's much smaller than 1 for these initially super horizon nodes. So the full spectrum, the peak of the spectrum is going to be set by the maximum bubble size. And we can show that this is approximately what it is. So putting all this together, so for values of k greater than the peak value, we have the subhorizon expression. For values on the other side, okay, so the derivation for the subhorizon nodes goes all the way up to the peak. For the superhorizon nodes, we actually do need to make an approximation that makes it valid only, in the farther superhorizon regime. So there's some finite, k interval between the peak and some value of k that we call the breaking scale, where the power law is going to be something different. And we need to join these things up, and you can probably do this more carefully. But just as a first pass, we're just going to assume some sort of power law linking these up, which you can see in this plot. So this is 2 example tensor power spectrum. So this is for a 3 keV benchmark. Keep in mind that this is occurring in some dark sector, but here T is going to be just kind of like a proxy for time. So yeah, so this is the 3 keV benchmark. This is the subhorizon scaling. This is the superhorizon tail. And then this thing that has a slightly different slope is the region that we've just joined them up with a power law. So that's 3 keV, and then this is 1 keV. And the values of alpha here are 0.05 and 3 times 10 to the negative 5. These are chosen both to saturate, well, they're chosen to be consistent with various constraints that we have from, say, scalar perturbations or delta and effective. And also because, as you'll see in a few slides, they're going to give us maximum amplitudes that are kind of, comparable with inflation with a tensor to scalar ratio of 10 to the minus 3. Right. Oh, one other thing, this gray CMB sensitivity region. This is kind of the domain of support for that window function kernel thing that I showed earlier, the epibel squared. So if you'll remember, the CLBB was like a integral over the tensor power spectrum times that window function. So really the only regions that are going to contribute from the tensor power spectrum are going to be the overlap with this gray region. So in the 3 keV benchmark case, we're going to be doing everything with the tail of the tensor power spectrum, and then for the 1 EV benchmark, we'll be sampling
so when
from.
you say when you say CMB sensitivity, this is the CMB sensitivity to the primordial gravitational waves?
Yeah, I don't really like calling it this. It's more like the region where that kernel has, some non-trivial value, which kind of matches up with the CMB linear sensitivity region, I guess. But
so the reason I'm asking you, because if it's, you do have some more bounds on the scales from Lyman alpha and CMB spectral distortions, and
yeah, absolutely.
so those does not enter in your gray shaded region, or is it just the CMB?
No, those constraints definitely do enter, and it's why we've had to take such tiny values of alpha, because we are doing this, at really late times where we have these constraints from Lyman alpha and spectral distortions and whatnot. So yeah, we do consider these when we take our phase transition parameter values, and it's why we've had to choose these kind of contrived combinations that, these aren't derived from some finite temperature effective potential. I would ultimately like to show that they can come from one, but at this point, we've just chosen them to be consistent with those constraints and to give us a signal.
And this alpha is basically the latent heat.
Yeah, it's essentially the latent heat.
But then why is it so small? Because I thought for supercooled phase transition, this has to be at least larger than 10 or 100, no?
Yeah, no, those are definitely typical values for the latent heat. We've had to take them to be so small. Again, this is completely artificial. This isn't coming from some microphysics model. I would expect something like value 10. We've had to take them so small just not to violate various constraints because we're doing this at such late times. But
yes,
yeah,
so
this definitely is not a natural value.
Yeah, so that I understand, but then why do you call it supercooled phase transition? Because alpha.
Because the beta on H is like ordered 2 to 5.
Okay, fine. So beta by H is just the duration of phase transition, right? Whether phase transition is happening very fast or very slowly, right? So this is not really tells you whether it's supercooled or not. It just tells you whether it's a very slow phase transition or very fast phase transition. So the quantity which tells you whether it's supercooling is the alpha. I mean, if it's large, whether it's really cooling a lot or not, right? Because the latent heat is the distance, the height between the false vacuum and the true vacuum, right? So if it's large enough, then you have a lot of energy going from the background to this from the system to the background. So that's when you supercool.
That makes sense to me.
So I
yeah,
would
no, that does make sense. I've always kind of used beta on H as a metric for that, just because. But that does make sense. So maybe this is a bit of a misnomer to call it that in that case.
I would simply call these phase transitions slow phase transitions. That's all.
Slow. Yeah, that might be better.
Okay.
I see what you're saying. Okay, slow phase transition. Okay. So that's what the tensor power spectrum looks like, and now we're going to see what the B mode signals look like. So this is for that the later time benchmark of 1 eV. So you can see that it peaks indeed on smaller scales. So for the inflationary case, typically it peaks around 100, multiple of 100, corresponding to recombination. This thing is going to peak at slightly smaller scales, but not that much smaller because 1 eV is pretty late. Again, we've chosen the parameter values pretty artificially just to give us, matching with inflation with a tensor to scalar ratio of 10 to the minus 3. So the top plot is just the angular spectrum of B mode polarization plotted in terms of the DLBBs, and then the bottom is the ratio between this and inflation. So you can see that, indeed you peak on smaller scales, and then on larger scales, there's essentially nothing. So this can really be understood from looking at the shape of this. So in the inflationary case, you're flat. So the shape is really going to be determined by that kernel function, and that kernel function peaks around a k of 10 to the minus 2, and then falls off slowly on larger scales and falls off really, really quickly on smaller scales. So that explains the inflationary case. But for the tensor power spectrum, from the phase transition, the peak is coming at smaller scales. So even though f of L is suppressed here, we get most of our contribution from here, which explains why it peaks slightly smaller, and then less power on larger and smaller scales because the shape is a triangle. The other one So in this one, all of the power is coming from the tail of the distribution, which goes like k cubed. So this one's going to peak at much smaller scales. As a reminder, this is the 3 keV benchmark. And it's also going to be less powerful just because FL. So essentially, the earlier you're trying to do this, the smaller the signal is going to be, just because the kernel thing is going to be suppressed on those smaller scales. So for this one, we're actually comparing with tensor to scalar ratio of 10 to the minus 4, which is kind of the most optimistic.
Can I ask you one question? So is it correct to interpret that you are computing the anisotropies in the gravitational wave background? So this is not like the amplitude of the gravitational wave, right? This is the anisotropies of the gravitational wave background, and just like this, like the CMB.
Yeah, I think that's correct.
So basically, when you showed the formula of the phase transition with beta by h to the power -2 something, so that was just the amplitude, right? And this quantity, which is BB modes, d of BB modes plotted as a function of L, this is basically the anisotropies in that stochastic gravitational background.
I haven't thought about it like that, but I guess so.
Okay. So then, you don't need to only concentrate on the CMB scale. You can also do it for you can do it for other scales where, like with LISA detector can be important, or Einstein telescope can be important, even pulsar timing array, because just like CMB, if it measures the BB modes, it can distinguish among various anisotropies and modes, multiples. There are prospects to do the same thing with LISA, and so you could provide very high scale phase transition.
Oh, yeah, I see what you're saying with the gravitational waves themselves. Yeah.
That's actually what you're plotting, right? You are basically plotting the BB modes, but you are plotting with L, which is basically the anisotropies in the gravitational wave background.
Yeah. So this will look different in a plot of just, the spectral density of these tensor perturbations as a function of K. Yeah, so these guys are, at frequencies much lower than LISA or anything really that we have right now.
Yeah, but
it's like a different way to process the tensor perturbation is the way that I've been thinking about it. Instead of
yeah, true. So what you're saying is true, but I'm saying that whatever CMB is able to do, LISA will be also able to do, because basically it's a measurement of the anisotropies of the background. In fact, to some extent, so it will only boil down to, if this is true, I'm not sure if this is true, then it will be only boil down to your choices of T star. So for CMB, you needed T star to 3 kV, and therefore for LISA, you might be interested in the electroweak phase transitions, like GeV scale or TeV scale. Anyway, maybe we can talk about.
Yeah, maybe I need to think about this a little bit more. Maybe we can talk offline.
Yeah, sure. So sorry, please go ahead.
Oh yeah, shoot, I'm almost at time, I guess. But I think these two plots are. Can I go like 2 minutes over to show the gravitational waves?
Yeah, sure, please.
Okay. Right. This is just that's in our paper. I think I've already gone through how to understand the spectral shape of these guys. But the gravitational wave signal is the way that I've been thinking about it is, this is another way to process the tensor perturbations that you might not have thought of. And it's, at least for this source, it's only relevant for these super contrived late time things. So maybe there's a reason you haven't thought of it, but honestly, I'm surprised you can see anything at all. The more natural thing you might have thought of is the probing these via the contribution to the stochastic gravitational wave background. As parameterized by this spectral density parameter. So the energy density in gravitational waves per log K normalized to the total energy density. I won't go through how to compute this in the interest of time, except to say that it's really analogous and also a little bit easier. And also that should not be 13. That should be like 1 to the third. This is the approximate expression for the spectral density today. And then this is what the plot looks like for these two benchmarks. So yeah, as I said, you're peaking on much lower frequencies than say LISA or square kilometer array or really anything right now can probe. But we needed a lot of power in these things, particularly at earlier times, in order to get an observable B mode signal. So even though it's peaking at lower frequencies, the sub-horizon tail is pretty strong. Okay, and that's essentially it. I'll end maybe 2 minutes late with the summary slide. So the main point is that we should be considering possible contribution from these other sources that you might not have thought could pollute your B mode signal. So here we looked at a first order phase transition, and we saw like a proof of principle that maybe these can actually produce B mode polarization on the observable scales if you have the right values for the phase transition parameters, which it's an open question of can you actually get those, but the signal strength can actually go up to values that we hope to test in the near future with CMB stage 4 and Lightbird and Simon's Observatory. Nevertheless, you can distinguish this scenario from inflation because you're going to get a different shape for the power spectrum. So provided you can make measurements on multiple angular scales, you can still distinguish this scenario. And then another way is, the gravitational wave signal can act as a cross check. So if you see something in the B mode signal, but you don't see something with gravitational waves, then it's inflation. But of course, this is hard because, we can't see this low frequency in gravitational waves yet, but that's kind of what you need to get an observable B mode signal in the CMB. Yeah. So